Thank you, and welcome to this little workshop. Hopefully we're going to have some fun today, and I hope you all brought your equipment, because this is a hands-on thing, so we're going to do some exercises together. So, without further ado, let me introduce myself a little bit. So, my name is Espen Sande Larsen. I've worn about just every hat that this industry has to offer over the course of 30 years. I'm also a professional musician, and I have 3 kids, and I'm an uber geek. I love everything that has to do with programming, hacking, hardware, tinkering, everything. And I also love drinking beer, which is why you should never have a workshop the morning after the party. That's just a mistake on my part, but hopefully this will be okay. And I also work for this little bank up in the Nordics called DNB Bank. And since I do work for a bank, even though I don't know anything about banking or finance, I'm actually horrible at that part. I work for the R&D department as a researcher into security research. But because I work for that bank, I have to have this slide. So just have a read through. I don't know what it says. Basically it says something like, what I'm about to say is my opinions, not the bank's opinions. Yeah, that's that. It's just something I have to do. So what is this workshop thing? We are going to learn about hacking, doing exploits, and breaking into systems. You're going to get introduced with some tools, some techniques, and some processes. And you're going to do this by solving challenges that I will give you. So hopefully that is something that's going to be fun. But before we can start hacking, we have to know what is actually hacking. How does it work? What is it? Well, why take my word for it when there's so many great examples in the movies and television of what hacking really is? Look at this gem from the show NCIS.
No way. I'm getting hacked.
And that's how you know you're getting hacked, because there's 1 million pop-ups on your screen.
They've already burned through the NCIS public firewall.
Well, isolate the node and dump them on the other side of the
And what's better than defending in real time on one keyboard with one defender? That's 2 defenders on the same keyboard, because that's how keyboards work.
I can't. It's a point attack. He or she is only going after my machine.
It's not possible. This is DoD level 9 encryption. It would take months to get built.
Hey, what is that, video game?
No, Tony, we're getting hacked.
If they get into Abby's computer, the entire NCIS network is next.
I can't stop him. Do something, McGee.
I've never seen code like this.
I haven't seen code like that either. It's another thing.
Where'd it go, Abby?
I didn't do anything. I thought you did.
No.
I did.
That's how you solve that situation. Because in this government agency, all essential files and information the hacker was after was in that single terminal in the lab. So yeah. Or what about this show? It's CSI New York. Listen carefully. This is a gem.
For weeks I've been investigating the cabbie killer murders with a certain morbid fascination.
This is in real time.
I'll create a GUI interface using Visual Basic. See if I can track an IP address.
I'll create a GUI interface using Visual Basic to see if I can find an IP address. I don't know how to comment on that. It's just silly. How about a movie that's named Hackers? Surely they had to do some research, right? Let's see.
There's a new virus in the database.
That's how viruses work.
It's replicating, eating up memory. What do I do?
Type cookie, you idiot. I'll head him off at the pass.
We have a 0 bug attacking all login and overlay files.
Run antivirus. Give me a systems display.
There's your systems display. Let's shoot the hackers in 3D.
Die, dickweeds.
A rabbit is in the administration system.
Send a flu shot.
Rabbit, flu shot, someone talk to me.
A rabbit replicates till it overloads a file, then it spreads like cancer.
Cancer?
Yeah, no. Do your keyboards look like that? These little circle things with no symbols on them? No, of course not. How about a show that was made about an actual hacker who lived? They had to do at least some levels of research, right? This is from the show Scorpion. So just to set the stage, there's malware on that airplane, so they have to patch it. And the only way to patch it is to chase the plane down the runway, get a member from the flight crew to climb down on the landing gear.
Drop the cable! Drop it now! Come on, we gotta get it now! Freeze!
With an Ethernet cable, because that's how you patch airplanes.
What's it say?
I don't know, a few seconds. It's a few
We're running out of room!
There's a few seconds. Almost. Oh, no. Hold on. It's going.
Stretch! That's one durable laptop, that's true, yeah. I actually tried to put in a purchase order for a Ferrari in case I ever needed to patch an airplane, but sadly my boss didn't approve it. But yeah, you know, well, that's life. Now, all these examples are silly, and this is not how hacking actually works. But hacking used to mean something different back in the day when I was starting out with technology, because hackers back in the 70s and 80s, it wasn't these malicious actors who did bad things. It was all about tinkering with things and thinking outside the box and trying to make the best of the components you had. It was like they built computers, they made phones do things they weren't supposed to, and things like that. One of my favorite examples of this is Steve Wozniak, who built the color circuit for the Apple computer, the first one. And he figured out if he modulated the signal to the cathode ray tube, he can make that beam misalign with the phosphorus cells in the screen. And by doing so, he could make consistent colors, not that many colors, but some colors consistently. And that way, that computer had a color output screen without any form of video interface. And back then, what we now refer to as hacking or hackers was known as freaks with a PH, because in those days, in order to talk to a computer, there wasn't any internet and things like that. You had to call it up on the phone. That's because that's why there's PH in the word freak. And if you broke into systems and servers and other computers, you were a freak. But these days, you're now known as hackers. And what we mean when we're saying hacking is basically exploiting systems through some kind of vulnerabilities. And just a little audience poll. How many of you are developers? Great. How many of you are architects or solutions leads, text principals? Awesome. And how many of you are like security professionals? You work with pen testing, you're a CSO. Okay. Maybe during this workshop that will change. And how many of you are something different, like a Scrum Master? Wow, no one. There's always one brave soul, usually, who says, I'm the Scrum Master. Awesome, cool. Let's talk about the different motivations that hackers have and why they do what they do. Because you can always identify hackers and their motives by looking at these lovely colored hats, because that's what they are wearing. So we have the black hats, that's the malicious people, that's the bad people who do bad stuff. Then we have the white hats who do things for good, they do things for ethical reasons, they test their own systems, so they're hired to break into systems and things like that. Then we have the gray hats, that's kind of in between. They don't necessarily do things for malicious reasons, but they do things because they can, and they gamble that they would rather be rewarded for disclosing their findings rather than being litigated. And then there's the green hat, that's the new hackers who has just started their hacker journey, which is something I hope to inspire you all to do today. We have the red hats, that's not the Linux fan people, but it's people who hack other hackers and take down big hacker organizations. And then we have the blue hats, and this is a special kind of hacker because they are usually invited by software, independent software vendors to look into their systems before they are released into the wild to see if there are any 0 days or any kind of things they need to fix before that goes wild. Microsoft, for instance, has a long history of hosting these blue hat invitational events before releasing new versions of Windows or Office or any of the big things. And let's talk about why these hacks happen. Why are our systems being broken into? Well, we are humans. We make mistakes. And we don't necessarily make those mistakes on purpose, but those mistakes are made because software systems are quite complex and they have a lot of details, and there's almost impossible to have the complete overview of everything that's going on. And the devil break into your system, that's always in one of those small little details you overlooked. It's also, these days, we love other people's code because that's code we don't have to write ourselves. Just think about all the libraries you use, and I'm talking to you JavaScript people because you love other people's code. You like millions of lines of other people's code. And it's also, we kind of like our tools so much that we try to use them for everything, even though they're not intended to be used that way. It's kind of like if you have to build your foundation for your house and you need to mix the concrete, you still use your hammer because you love your hammer so much. It's so easy to use, it's so familiar to you, even though that's not the best tool for that job. And I learned this the hard way. And I will promise you that this little picture of cinnamon buns will make sense in a bit. Because this was a long time ago, but I got a new job. I got to be the CTO of this startup. And this startup was going to take over the world. We were all going to get filthy rich. And, well, that was the hope at least. And we had to put in an insane amount of effort and work in order to build this thing. The product was this online ad platform that should run on online newspapers across the world. So the idea was that if we have all of these ads and they are interlinked, and you can play games, and you can build high scores, you can win prizes, and we had this entire system that would back that up. The problem was that back in those days, this was before there were any clouds. So I essentially had to travel around the world and build my own cloud. I had to set up data centers across Europe, in the US, and in Asia, and build up this network system and the back end. And when you wanted something to be like this, where you had like games and stuff in the front end back then, there was only one thing you can use. Anyone want to guess what that thing was? Flash, yeah, that's true. So Flash, for those of you who don't know, is this kind of strange programming, rich media content creation thingy. You had code, and you had also animation tools and drawing tools, and it was not really meant to create secure systems. But it's the only thing we could use to build that front end, because that was the only thing available. So we did. I did voice my concern, saying that, well, essentially all the important code is running on the client side, meaning that if somebody, for some reason, could like decompile that somehow, they could probably figure out something that goes on in the back end. And that happened. And what happened was that we had this big campaign in Sweden with one of the convenience store chains, where you could play this game where you would kill flies, and if you killed enough flies, you got a coupon and you got a free cinnamon bun. And a Swedish student decompiled the front end and found the back end call to generate the prize tickets, created this little application called the cinnamon bun generator, spread that on the university forums, and I got a call early in the morning, like 5 a.m. or something, that one student had picked up 73 cinnamon buns in one day. My immediate response was that, well, that person is really committed to cinnamon buns, which my boss didn't think was funny. And the end of the story is basically after I had to stand in front of the board and say, I'm sorry, it's my fault, this will never happen again. And then I kind of changed because I didn't want to get yelled at anymore. So I said, you CEO, you bring a newspaper and you find this individual and you bring a big case of cinnamon buns and you find him and thank him with a big picture for finding the vulnerabilities in their system. So that was kind of like this impromptu bug bounty program. And my CEO did. And we had this big spread in Sweden. A little detail to that story is because I told this story earlier this year at a conference in Sweden. And after the conference, this guy came up to me and was like, "You are the cinnamon bun guy." I was like, yeah, that's me. I wrote my master thesis on your colossal failure. Which is, okay, thank you. And that's now part of the innovation studies in Sweden and the textbooks. Okay, so I've literally created the textbook example of what not to do in Sweden. So that's quite a feather in my hat, I guess. So anyways, and the scope of those cinnamon buns, it was that it wasn't just 73 cinnamon buns, because evidently I had served the entire student body of Sweden free cinnamon buns for like 3 months or something like that, but who cares? Yeah. And how can we prevent these things from happening? How can we learn about how these things are done? And a great way of learning offensive techniques and hacking is something called CTFs. Are you familiar with CTFs? Yeah, capture the flag. I will let Mr. Elliot from Mr. Robot, the only show on television that gets the hacking parts somewhat right, define it for you.
A CTF tournament, capture the flag. It's like the Hacker Olympics. Teams around the world compete to solve challenges, reverse engineering, protocol exploitation, forensics. The entire city's suffering an energy crisis while they're here exercising their inner anarchy.
So you get to exercise your inner anarchy by solving challenges, which is kind of fun. And this is what we're going to learn today, how to solve these kinds of challenges. So what are CTFs? It's basically this gamified way of learning how to break into systems, how to break codes, how to think differently, how to exploit systems and poke at them and figure out what's wrong and how you can get in. And since it's gamified, it's an incredible catalyst for learning stuff. And the cool thing is, once you start to think this way and once you start to learn these kinds of skills, you start thinking differently about how you build your systems as well, which is a cool thing, because that means that you will make more secure systems. And you do this by solving these little challenges, and each challenge is designed to kind of teach you and guide you into a certain set of scope for breaking into something. It could be just as simple as breaking a cipher, but it could also be as involved as taking over an entire service or an entire server. And the cool thing is that if you do this in your organization, security, hacking, and all of these things will suddenly be on the agenda. It's something you will think about every day. We actually had Capture the Flag in DNB, the bank where I work, and we'd open it to the entire group, not just the tech teams. And we did that for Cybersecurity Awareness Month last year. And what happened is that the coffee machine and water cooler discussions were suddenly all about breaking into systems, all about SQL injection, cross-site scripting. People were really, really engaged, even the people who are not really technical. And my favorite email I ever got in DNB was this lawyer from the legal department who sent me a letter of apology. And it said, "I'm so sorry, but I did a SQL injection attack on one of the challenges and I accidentally deleted the entire database. I am so sorry." And when your lawyers in your legal department are performing SQL injection attacks on your systems, you're doing something right, in my book, yeah. And it's also just fun to be on the dark side for once, right? So let's check if you we're going to solve these challenges. Challenges and CTFs, they are usually in different categories. So we have crypto, that's not bitcoins, it's about breaking codes and breaking encryption. We have stego, that's steganography, and that means you have something that's hidden inside something else. It could be like a binary file, but it's hidden inside an image. Or it could be music that encodes data. It can be many different things. These are all about making you think differently. Then we have forensics. That's like classical data mining, where you get like a file system, network logs, and there's some kind of secret inside there you have to figure out how to find somewhere. And then we get into what's one of my favorite things, that's reverse engineering, where you have to take some kind of program, figure out how it works, and see where it's vulnerable. That's kind of old school hacking. It's not that important anymore. It used to be more important because things wasn't online previous. So that's how you would crack software, or how you would make your games run for free. And then we have, usually it's called either vulnerabilities, sometimes they call them supply chain attacks. It's basically where it's not your code that's the problem, it's somebody else's code that you used as a dependency in like third-party dependencies. Could be like servers or libraries and things like that. There's usually a whole category for the web itself, because the web is this wonderful, wonderful complex thing with a bunch of vulnerabilities all on its own. And then there's a creme de la creme category that's called pawning, where you actually get to take over an entire system and control it the way you want. Usually some kind of shell access or some kind of way to execute arbitrary code. Let's do a little tool check, because for this workshop to be effective, it's important that you have your laptops ready and you have some tools installed. So hopefully you will have some way to run x86 code in a Linux environment somehow. So either a virtual machine, or you're running Linux natively, you're dual booting, something like that. It's important. You will need Docker, because the labs is this big Docker thing that you have to download and run. A lot of the things is on the web, so hopefully you will have a browser. And there's some tools that you're going to use. We're going to use John the Ripper to break into different password files. We're also going to use the wonderful, excellent GDB program. That's the GNU debugger. It's old school, but it's good school. It's really fun. There's a version of GDB that's called Pawn Debug that has some extra tooling that will make reverse engineering and doing all the binary exploits more easy. And we will use Python to script things, because we're going to use pawn tools for some of the exercises. So hopefully you have all of this somehow configured on your machines. So before we continue, I'm going to give you a little bit of time to get that up and running, or check that you are there, and I will make my way through the room just to, if anybody needs any kind of help for some reason. Yeah, browser can be on your native operating system. As long as you can network into your Linux container, it's fine. Hello? Yeah, so if you're on Apple Silicon, you will need some way to emulate an x86, because the instruction sets are different. Yeah, UTM is a good option. Yeah? Well, I would advise you, if you're running Kali, to run it in a VM, because of the tool sets. Great. So some of you are installing Linux, some of you are running up your VMs, some of you are finding some kind of virtualization environment. So I'll give you some time before we continue. But I'm going to give you a little QR code as well, because this is where your lab exercises will be. It's a GitHub repository with a bunch of Docker containers, so you can pull that down, and that's the thing you will be working on trying to exploit. The QR code been deactivated. That's fun. Okay, ignore the QR code then. It's just github.com/drcircuit/wch-hack. Guess I didn't pay my bills. So just to show you, this is the files you will be getting once you have pulled down that repo. In order to run it, you just run docker compose up. It will build all the images and containers and run it up. This is like a little mini CTF with a bunch of things. Once you have run it, you should be able to just go to localhost. It's just regular localhost, and you will be able to create a little profile. If I do that. And once you're logged in, you will see some challenges. Oh, okay. It's Compose is a plugin package you have to install. It's called Docker Compose plugin. Yep. Yeah. So if some of you are having that issue, it's because I built this thing on Windows, and Windows doesn't care about casing in directory structures. So if I end the slideshow, and I can show you. So if you list this thing, you can see that this one thing is called Citadel with a uppercase C. So if you have some problems, you can just change the Docker Compose thingy. Here it's lowercase c, so if I just change that to uppercase C, it will work. And it will work again. That's my bad. So let's start the first section. This workshop is divided into 3 sections. We're first going to talk about cryptography, then we're going to talk about binary exploitation, and finally web exploitation. So we're going to start with cryptography because it's kind of this easy path into this whole thing. And we're going to talk about encodings, different kinds of encryption, and there's some tools you will use as well. One is Python, because we're going to write some little Python scripts to break some codes. There's also this great web page called decode.fr. It's a French page, but it has English, thankfully. And there's also this little Swiss Army knife of dealing with code or encryption and encodings called Cyberchef. That is very beneficial to solving these things. Before we get into encryption, let's start talking about encoding, because encryption and encoding, they go kind of hand in hand, and for some it might be a little bit hard to see the differences. So encoding is just a way of representing data in a different way. You can convert encoded data in different contexts, and it can take on various forms. There's several different forms of encoding, and they all have different intentions, but the thing is, you always have to remember that encoding is never encryption. Even though it's hard to read for humans, it's still plain data that's openly readable. Here are some common encodings. We have a classical Morse code. That's a form of encoding information into sound. We have ASCII, UTF-8, URL encoding that we use online, HTML encoding, and there's also binary encodings and different ways to represent data, like base 64, base 58, base 32. Let's take one example, for instance, Morse code. So Morse code, you use dots and dashes to encode a form of text. And you have different sets of pulses that you can read over the line. And it's something that's still used today. It's used in communications on the sea, in the military, and things like that. And it's used all the time in CTFs, but it can also take some different forms. One example I saw recently was in Google CTF this year, where they had emojis representing the Morse code. So that can happen. And it's basically like this. You have a set of symbols that means a letter, and that's sent as audio pulses, either short or long. Then we have a much more common encoding that all of you hopefully will be familiar with. That's ASCII. That's a way of representing text on a computer. It's a 7-bit way to represent a bunch of characters. It was developed back in the 60s, and it's basically the foundation for how we view text on a computer. And it's kind of cool because it has some nice properties. For instance, uppercase A is 65 and lowercase a is 97. And because they are exactly 32 numbers apart, you can do all these nice bitwise things to convert between the casings and things like that. For instance, if you end with a complement that flips all the bits, that will get you from lowercase to uppercase. If you OR it, you will get from uppercase to lowercase. Or if you just want to change the casing, you can just XOR with 32, and you will be able to change back and forth between those casings. And the next encoding that we're going to need to know about is URL encoding. And that is a way for a browser to be able to have text and then have some kind of information that is encoded because it shouldn't interfere with the address you're trying to access. And what they do is they have this way of representing special characters with the hexadecimal representation of the characters in hexadecimal number format, and it's prefixed with a % sign. So for instance, space will be %20, or exclamation mark will be %21. This is also something that you need to take into consideration, because in some of the challenges you will see these pop up from time to time, and you will always recognize it by seeing that % sign. Then there's also base 64 encoding, which is a really fun way of encoding data. So you have 64 safe characters that you can use. So you change your data into a 6-bit format, and then you divide that into 3-bit chunks, 3-byte chunks. and you use that alphabet to represent it. And you can do that the other way and back. You always have to pad it so it's divisible by 3 in order to encode or decode it. So it works like this. So let's say you have the word hacker. So those are the binary representations of those characters. You split that data into 6-bit chunks. So these are now 6-bit long. And then you just change that to one of the 64 characters that you are. So you end up with this little string, this strange string right there. And you add the equal signs, that is padding. You just add enough padding so that it will be divisible by 3 when you're doing it back. So the next thing we need to do when we go to the next stage from encoding, we have something called hashing. Hashing is a way to take a piece of data and have a steady function to convert that into some kind of fixed value. The data you have hashed is not doesn't persevere through that process, but it will always create the same value when it's hashed. And that's the way to do some kind of data integrity tests. It's a way to have a way to check if something is correct on 2 sides of something without either side knowing the actual data that's present. It's a way, for instance, to check if your key and my key is the same key by only checking the hash of that key, so we don't need to exchange the key itself. And one thing that is really important to know is that hashing is not encryption, and it's not a guaranteed unique value because there are collisions in these functions. And it does not preserve the data you are putting into that function. It's used for a bunch of different things. It's used for password storage, data integrity checks, cryptography, signatures. It's used in blockchain. It's used for shortening URLs. We use it for caching as key values into a cache. And we also use it to check files and to check their integrity after they've been transmitted somewhere. And there are a bunch of common hashing functions. We have MD5, which is a very classical one that you should never use anymore because it's been broken to the degree that it's no longer safe. Then we have SHA-1, SHA-256, SHA-3. There's also a CRC32, which is a cyclic redundancy check used on your file systems. We have HMAC, which is this keyed hashed message exchange. We have also bcrypt and Argon2. There are a bunch of different things. And the thing is that none of this is encryption. It's just a way of getting a value from something and have that always be deterministically the same thing. I remember once I was the tech lead on this dev team, and one of my devs said he had created the ultimate encryption. So what he had done, he took some input data, he did a SHA-2 hash of that input data, then he took that hash, did a SHA-1 hash of that, then he took an MD5 hash of that hash, and then he took a DES hash of that final hash to get a little tiny piece of data. Which means that what he had essentially done was taking something that had like 1 in a billion collisions and turning it into something that would have 1 in 65,000 collisions. And that's not beneficial. He didn't really encrypt anything. And that system actually cost that business a lot of money because of that mistake. So now we're talking about encoding and hashing, so let's talk about actual encryption, because actual encryption is all about protecting data. That's where you change something that's plain and you end up with a cipher that is a hidden message that you have to have some kind of key to decode or open. There are many different ways of doing this. There's a bunch of algorithms. There's also a bunch of strategies for doing encryption. For instance, we have like rotation ciphers where you shift characters by some kind of fixed number position key, where you just skip into the alphabet and take that character in place. There's substitution ciphers where you take some way of jumbling up an alphabet, and then you just use that as a key index into encoding your text or encrypting your text. And then we have the things that start with keys, like symmetric encryption, where you and me, we agree this is the key we're going to encode or decode our messages with. And as long as we are the only ones who know that key, it will be nearly impossible for a third party to decode the data in transit. And of course, there's also asymmetric encryption, where we have the notion of a public known key and your own secret private key, which is one of the things we're going to break in a little bit, which is kind of fun. Asymmetric encryption is the foundation of everything you're doing online whenever you're talking to through a secure channel. And you use it usually to exchange a generated key that you will use for symmetric encryption on the other end, because asymmetric encryption is kind of costly and symmetric encryption is much less data intensive. So let's talk about some common encryptions. We have the classical ciphers. That's like the Caesar cipher. Are you familiar with the Caesar cipher? Some of you, okay, yeah, cool. So the Caesar cipher is basically where you just shift the alphabet in some direction. You wrap around if you go past the last letter. So it's like this. Some of you maybe have gotten this kind of decoder ring or something in a cereal box or a comic book. So basically what you do is you set 7, that's the offset, and you check, okay, I want to write A, well that now corresponds to H. If you want to write S, that corresponds to Z, and you just do that by shifting the alphabet. It's named after Julius Caesar, and it was extensively used in the Roman period by the military back in the day. I remember one story about this guy, this soldier. They shaved his head and they tattooed all the message on his scalp, and then they put a helmet on him, and then they sent him to send his message, which is kind of not really optimized solution, because there's just so few messages you can send that way before you run out of heads to send to your leaders. Anyways, it's a fun cipher. It's an easy cipher. It's not secure at all because it can be easily brute force, but it's the most basic form of encryption you will encounter. It's kind of the foundation. So next cipher we're going to look into is something called an @bash cipher. It's a little bit more involved. So it's also a substitution cipher. Basically what you do is you take your text and you reverse your alphabet, and then you just pick the corresponding letter. So it's quite easy, and it's easy to break, and it's even featured in the Bible. So for some reason it's a divine cipher, I guess, in that sense. But these techniques are pretty basic, and so as time progressed, they needed something much more involved and much more secure. So that is where we come up with something called a Playfair cipher, which is a little bit more involved. So it uses what's known as a digraph substitution scheme. Digraph is basically 2 letters that you combine, and then you think of your alphabet as this kind of matrix, and based on their positions in that matrix, you will figure out how to do your substitutions. So there's some rules. So basically you construct this matrix. You start with some kind of keyword. So in this case, the keyword is keyword. As you can see, keyword, and then just fill out the rest of the alphabet. Next, you take what you want to encode, and you divide that into bigrams or digraphs. So it's like this. If I want to encode the word hacker, I will divide it into bigrams, meaning 2 and 2 letters. Why people need to make these complex words to describe something simple, I don't know, but that's the term. So you have H-A-C-K-E-R. And then you have these rules. that you evaluate when you look up these letters in this matrix. If the letters are on the same row, meaning the 2 letters in the bar graph, you take the letter to the right of the letter you want to encode. If the letters are on the same column, you take the letter below. If they're not on the same column or row, you figure out where these letters are, and you find the rectangle or the square where these letters are in the corners, and then you take the opposite corners of that rectangle. So that sounds a little bit involved, but it's actually super easy. So with hacker as an example, you have HA, so they are on the same column. So we will select the letter below. So for H, the letter below H is P, and for A, the letter below A is H. So that means it gets PH. Easy. Next one is a little bit more involved. That involves this rectangle thingy. So here the letters are CK, so C is there and K is there. So we now need to like find the rectangle where those 2 letters are corners, and that is these 2, so R and O. So K goes to the opposite corner and becomes O, and C goes to the opposite corner and gets to be R. Easy. And the same thing with the last one, ER. You have E, so you create the rectangle where these are the corners, meaning that these 2 will be the other corners. So E goes to K and R goes to D. And with the playfair cipher, the word hacker using the word keyword as a key is this frocked. And that's the way that cipher works. And there are even more involved ciphers. And another one that's a fun one. It's called the Vigenère cipher, where you take it's also again with these words a polyalphabetic substitution, which is a fancy word for saying that you will use a keyword as a stream and you would use that to offset into an alphabet. It's actually much more easier than it looks. So we have the plain text that says attack at dawn. Sounds very military-ish. And we have a key that's lemon. So we just type lemon, 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 lemon. And then we calculate how far away is L from the start. That's 11. Okay, so A becomes L. How far is E from? Well, that's 4 spaces, so that means that T becomes X because you just add 4. So what makes this different from the thesis cipher is that every letter has a different offset, rather than having one single offset for the entire message. And this is actually the basis for a lot of encryptions that have been used through history. It's actually the foundation for what's known as the Enigma machine, but they had a much more involved process in calculating these different offsets because you can configure that machine in so many ways. So it wasn't consistently so as easy as this, where you just had the alphabet offset. And in order to break ciphers, we need to employ a skill that's known as cryptanalysis. And you can do that in several different ways. One is to do what's known as a frequency analysis to see if there are any letters that is popping up more frequently than others. For instance, in the English language, the letter E is a very common letter, so you will see that probably in a set of text, so it's easy to find. Then we have what's known as a Kaczynski examination. So for instance, if you take the Vigenère cipher, you will see repeated patterns in the ciphertext, and you can check out the distances between those patterns, and by doing so, you can calculate and derive portions or parts of that key. Of course, if you know some form of plain text that you expect to be in your ciphertext, that is a good thing to know, because you can use that to find where that's probably in the text, and then you can also figure out how to decrypt it. That's how they broke the Enigma code back in World War II, because most of the intercepted messages would start with some kind of weather report, so they look for words like rain, sun, weather, and by finding those they could figure out the keys and drive a way to decode the message. Of course, there's always the brute force attack where you just try everything and hope something works. And a much more involved and advanced approach is what's known as a side channel attack. That's where we use some kind of third-party information to figure out something about the key. One example I saw once was they checked the power consumption of a computer doing encryption and decryption, and based on the fluctuations in the power draw of that machine, they figured out which instructions that CPU was running, because each instructions had a different, tiny little bit of different power draw, and by doing so they could derive the decryption algorithm. And that takes a special kind of nerdy someone to do that, I tell you. That's beyond the scope of this workshop. And of course you can always just guess and and have some luck and figure out something that's beneficial. Nowadays we have much more involved encryptions that are a little bit more advanced than the ones you saw earlier. For instance, we have symmetric encryptions. That's where we agree upon this is the key that we will use on either side of this encoded channel where we're sending confidential information. And as long as that key is protected and safe, everything will be fine. One example of this is DES encryption, where we have a 32-bit key on either side, and as long as everything is secure, it will be fine and hard to break. It's not impossible to break, but it's hard to break. A little thing that's kind of not everybody is aware of, it's called the XOR cipher, or XOR encryption. It's a symmetric type of encryption, and the cool thing is that it's reversible, so you can either find out the key or the message by having either one of those kind of information. And this thing pops up in technology all over the place. It's used for serial numbers, it's used for passwords, it's used for zip files, and a bunch of different things that uses this kind of cipher. So it's also pretty easy. It's pretty weak, but it's very fast and efficient, so that's why it's used all the time. And it works like this. It's super easy. You have your ASCII characters, and this is why encoding is important, because a lot of encryption is a numerical operation, so we need a numerical representation of the text we're doing. And then we have a key. So in this case, we have the word hack and we have the word code. And we take the binary representation of those two things and we do an XOR operation. XOR is an easy operation where it's an exclusive OR, meaning that if the bits are set in a certain ways, they will end up masked and have a different representation. So in this case, 0 and 1, that will become 1. 0 and 1 will become 1. 0, 0 becomes 0. 1 and 0 becomes 1. And the rest is 0, because 1 and 1 is not exclusive, so that becomes a 0. And that is the basis for a lot of things that things are encrypted on computers, which is something that you will see in the labs. It's also something you will see when you start to break into systems for yourself. Okay, let's talk about the next one. That's asymmetric encryption. That is the concept of a private and a public key. So you take a portion of some kind of key that you know, and you take a section of it and you can publish it to the world. I can give that to you so you can encode messages, and since I am the only one who has the private portion, I am the only one who can decode it. It's the basis for PGP, and it's also the basis for RSA encryption, which is a very, very common encryption still in use today. And RSA encryption is depending on two large prime numbers. These are combined into a composite number, and that's your public key. And since factoring primes is a very hard thing to solve, especially when they're really big, that's why it's regarded as safe. And you just take your data, you turn that data into a number, and you do a mathematical operation. The operation is quite simple. So you choose two primes, big primes. You create a composite by multiplying those together. Then you create what's known as the Euler-Totient function, which is basically phi is p minus 1 times q minus 1. Then you choose an exponent. And that's a known thing. It's usually 3, 5, or 65,000 something. And then you do this little computation. And then you will do this operation on your data, where you take your exponent and your data, and you do a modulo operation. And you can share the E and the N, that's the exponent and the composite, and you have your own key to decrypt. So you just convert it to numerical, raise to the power E, take the modulo N, and you have your ciphertext. You can encode that however you want, and you can send it, and it will be safe. So that's RSA. Let's break it, shall we? Let's see if we can do this. Come on. So the thing about RSA is that it has it's hard to compute because factoring primes is what's known as an NP hard problem. Do you know about complexity theory and mathematics? Yeah, some of you. So NP is basically things that you can't compute in a feasible amount of time if they are NP hard, meaning there's not enough time left in the universe if you wanted to do this with brute force. Let's see. Let's go back. It's day 2. So, RSA. So, I have this little code. This is a super basic RSA implementation. So I choose two primes, I do the calculation, I choose my exponent, I calculate the totient, I have this super secret message that I want to encode, and I take that to convert that to a number. Yeah, I can zoom. I thought I could zoom. Is that better? So, yeah, again, choose two primes, calculate that composite number, choose an exponent, calculate the totient function, have my super secret message, and I convert that to a number by doing this bytes to long thing. I do the mathematical calculation, and I get my ciphertext, and I can print that out, and I can also print out the public key, which is the composite of the two primes. And since that is a very big prime, it should be safe. So if I run RSA, I get this is my ciphertext, and this is the composite number. So if I take that and I copy that, I will see if I can break it. So this is my message. My message, and this is my composite, big number. That's the N. Come on, why did I choose such a big number? Come on, yeah. So we have the number and the message. If you want to factor primes, one of the most efficient algorithms is what's called Fermat factorization. It's named after this French mathematician guy who lived back in a couple of centuries ago. And it's super easy. You just figure out the square of the thing, and you do this little thing. And I'm not going to go into it because that's boring. Basically, this is like, I have a number, what are the prime factors? There are several other algorithms you can use. You can use the Civ of Aristophanes. There's a bunch of other things you can use. But if this RSA encryption that I implemented was hard enough, this would take forever. So let me just save that. And let's see if it takes forever. Yeah, didn't take forever. So what happened now is it found the 2 primes. As you can see, those are pretty big. That's prime 1, that's prime 2. And this is the decoded message, and you can see it says super secret message. And the reason why it's easy to break is because there's one flaw in RSA encryption. And that is, if you look at these primes, you can see they share a bunch of digits. Can you see? So it's only like the last couple of digits that are different. If the primes are close enough, then it's trivial to break. If they are far enough apart, it's impossible to break. And that is why there was this big RSA catastrophe a couple of years ago, where they found this kind of flaw in one of the main libraries that was used for RSA encryption around the world. So, and as time progresses, the distance between those 2 primes can be further and further and further, and it's still easy to break because computing power is growing exponentially. So it's, again, super easy. A little standard algorithm, just knowing the public key, and I am able to break that message. And that's RSA encryption. So what the main RSA libraries now do is they calculate 2 super random primes and make sure that they are far enough apart so they can't be broken. So now it's time for you to do some labs. So I want you to do some of the encryption labs in the CTF. So let me see, go back. So you run Docker Compose up. If you don't have Docker Compose, you have to install it, and you can install it by doing apt install docker. I think it's compose plugin. If you do that, you will get Docker Compose, and you should be able to run Docker Compose up to set up the CTF and the portal. And in that portal, you will see a bunch of different tasks, and some of them are related to encryption. Let's see. And you will get into this hacker portal. If you're not logged in, you just choose a username and a password, and it should log you in. We have a couple of things here, like everything that's labeled crypto, like this, is a cryptography challenge. So let's see if we can break some codes. And what you do is you just click open. So here is something you have to figure out. You can use a hint if you want to. So for instance, this is something we have talked about, and it should look familiar to you. What you're looking for in all of these challenges is what's known as a flag. It's formatted like this, a $, curly braces, and some kind of secret. And what you do once you found it, you copy that, and you paste it in here, and you check your answer, and you exchange that for points. So once you've gotten your points, you know you have broken it. If you haven't broken it, it will say it's wrong. So I will give you some time to do these labs. And I'll be here if you have any questions to help you. Is everyone having a challenge logging in, or is it just some of you? Yeah, okay, yeah, that's the thing. Yeah, your password is too easy. Choose a more complex password. That's the key. I'm using a .NET thing, and I think it has this kind of password checker thingy. That's true. So just to show you, if you're having this issue where you're logging on and that just happens, you have to have a more complex password. Should work. Then you're in. Probably some UI things I could have done there to make it more easy for the user. But I'm a hacker, not a designer, so. Okay, if some of you are having the problem with the admin jokes container, I think it uses an old you can try one of two things. Let's see if I can find it. It's there. So what we can do is, instead of node slim, join node latest and see if that works. If that doesn't work, you can just remove that from the compose script. So just find admin jokes in this thing and just remove it. So let's start doing some more real actual hacking, because we are going to talk about binary exploitation. So how many of you are programmers, right? But how many of you are familiar with native binaries? Meaning they are written for the actual machine it runs on. How many of you work in some kind of managed language like .NET or Java or JavaScript, Python? Okay. That's cool, but there's something underneath the virtual machine, and that is the actual machine the code is running on. And that's what we're going to look into now. And for some of you, if you're not, how many of you are familiar with like computer instructions, memory maps, assembly? Okay. For those of you who are not, we just need to take a deep breath. It's going to be fine. It's not as hard as we're thinking. So to get into this, we're going to do what's known as reverse engineering, because that is basically what binary exploitation is all about. Binary exploitation falls into two main categories. One is reverse engineering, where you have to figure out how a piece of software works, what its design flaws are, and how we can exploit it. And then there's the other side that's known as pawning. That's where you find some kind of quirk or bug in the system, and that gives you the ability to take over an entire system and basically own that machine. So we're going to start with reverse engineering, and what we're doing is we're looking for some kind of information that tells us something, either by how it's designed or how it is put together, and see if there's anything there we can exploit. It could be as easy as just finding a piece of plain text string inside that binary, or it could involve that we have to debug that thing to figure out how that program flows. We need to maybe disassemble or decompile that binary to figure out how it's built. And we can create patches, and we can do changes to that binary to do. And for this to work, we have to decide on what kind of machine we're working with and what kind of instruction set. So for the scope of this talk, this is what we will be working with. We will be working with the x86 32-bit instruction sets. That means the Intel CPU platform. It's not the best system, but it's a good system and it's well known. That's why we're going to use it. We are going to use Linux as the basic operating system and the basic I/O calls and operational instructions we're using. And there's a concept called endianness in systems. That's basically which side of a compound bit is the most significant one. And for Linux on an x86, it's what's known as little endian, meaning that the last bit is the most significant bit. So, for instance, a memory address in little endian will be reversed compared to what you're expecting. We will need to know about the notion of the stack and the heap. That's the memory of your running application and how it's organized. And we will need to know about the different CPU registers. And we're going to use some nice tools that you will need to download to do these challenges. We have GDB, that's the GNU debugger. It's an old debugger that's used in native development. It's awesome, it's super cool, it's terminal based, there's lots of colors, and you can see everything about your binaries, everything from how the memory is organized to the instructions, and you can do a bunch of cool stuff with it. We're going to look into that in a little bit. We're going to use pawn tools, which is this Python library that you can use to exploit binary files. It has a bunch of different kinds of cool functions and things you can do in order to orchestrate exploiting binaries. I'm going to show you another lovely piece of software that's called Ghidra. Anybody know Ghidra? One of you, cool. So Ghidra is this wonderful, wonderful, wonderful present from the NSA. That's the National Security Agency in the US. And they decided to open source their main reverse engineering tool, which can take binary files and it doesn't just disassemble them, it actually decompiles them into a pseudo C-like syntax, which is super cool. And there's a tool called file, which basically gives you some basic file information, and there's a command called strings that can read out strings. So you will need to have an x64 Linux machine. You will need to either use UTM on Mac, a Cloud VM, WSL2, or some kind of dual boots. Most of you have this already, so that's good. You will need a basic understanding of C and C++. Hopefully that is okay with you. If you think C or C++ is this old thing, it's not relevant anymore because all the young kids are using Go and Rust these days, well, just think about what runs the internet, what is actually your runtimes built in, or what your libraries are actually written with. Because even though you're doing like AI stuff in Python, most of the libraries you're actually using is written in C or C++. And that won't change anytime soon. So, when we do reverse engineering, we follow a little process. We do what's known as recon, where we analyze and we run the software and figure out what is this intended to do. Then we do some tests, we check the inputs and the outputs, and we can look for clues. And what we can also do is we can attach a debugger. You can actually attach debuggers to code that you haven't written, other people's code. It's okay, it's fine. And you can figure out what happens to the memory, to the registers, and you can see if there are any ways you can exploit this thing. Finally, we can disassemble, decompile, and inspect the code itself and figure out what it's doing. So for instance, the recon phase, we do start with the basic thing. We just do file and on the file to see what kind of file it is. Next, we can look for strings. Use a string command to see if there are any basic strings that are beneficial to us. Then we can run the program to make a note of the inputs and the outputs. And we can use something called ltrace to see if it uses any external libraries that it's linked to and what information flows between the binary and that library. We can also check for system calls or syscalls using a tool called strace, where you can see if it calls out to the BIOS, to the OS, and does those kinds of things. And then we can use the GNU debugger to disassemble the program. We can step through it, we can set breakpoints, and we can do a bunch of cool stuff. Next phase is the identify stage. So did we find any plain strings that are beneficial? Are there any mismatched buffers? Meaning that you have allocated a certain amount of memory for a buffer, but you fail to check your input if that matches that size, for instance. That's a classical one. Are there any leaky details? Are you revealing that you're using some kind of third-party dependency that has a known vulnerability or something like that? There's also a bunch of common numbers that we developers love to use whenever we need some kind of random number. For instance, 42, we can see that in code bases all over the world. There's also this little thing called hex speak, where you can actually write some words using hexadecimals. So dead beef is it's not actually a number, it's a valid hexadecimal, but it's funny. And there's a bunch of other ones. One is disco babe or bad code, or there's a bunch of different hexspeak numbers that's used as constants all over the place. Us developers love to use these things. And also pi. Pi is a super, super classic thing that's used for these things, or some kind of, in the expansion of pi, some kind of little piece of that's chosen for some reason. Once we know this information, we can start to craft our exploits. For instance, if we have some strings, we can grep those strings. If we're found a mismatched buffer that we can overflow and exploit, and we're going to see that in just a little bit. Or we can see if there is any kind of algorithms that I can re-implement by patching this binary to make it do what I want to do. Like you can flip a bit in a if check to make it do what you want instead of not limiting you from doing what you want. We can calculate memory offsets. We can do a bunch of different things to figure out how can we control this binary. And it's also nice to know your basic bitwise operations. That can be super beneficial. Once we know this and we've crafted our exploit, we start by creating like a POC, a proof of concept, to test the attack. Usually in CTFs that you're doing with now, you get a local copy of that binary that you can test and work on yourself locally. And once you figure out how to attack it and crack it or break it, you can do that to the remote service, and you will get access to whatever you want to have access to. So there are a couple of different binary exploits that we can actually target. One is a funny one. It's known as a string format attack or a format string attack. How many of you are familiar with formatting a string with some kind of specifier and some piece of data, and it's get it interpolated and printed out? Yeah, that's benign, right? So in C we have this wonderful command called printf, this wonderful function. It's basically, it takes one argument and a multiple set of other arguments, and the first one is some kind of string with what's known as a format specifier. The next are the variable that will be inserted into that position in place of that variable. And that sounds benign, but the problem is that the way this actually works under the hood, because there isn't any notions or arguments or function calls really in the machine. What happens is that once printf sees that specifier, like this one, it expects that the next thing on the stack is the thing it can pop off and put in that place. As you can see here, there's no other argument, but there's still a format specifier, so printf will still, even though we haven't provided anything, it will pop the next value of the stack and try to interpolate that as a string. And if you're not providing that input, the user who's doing this can extract a bunch of information from your memory. So this is what happens. Sees %s, calls printf, and then pops the next value of the stack to try and interpolate that as a string. And also, printf and these format specifiers, they're a quirky bunch. They're usually some kind of type base that it tries to interpolate your value as. So you have strings, chars, unsigned integers, decimals, and hexadecimals. But you can also specify, I want to see the pointer, I want to see the memory address to that value. And there's this quirky thing that's not actually printing out something, but it writes a number of bytes back to the memory at that position, which is a very strange thing to have in a print statement, but it's there. It's probably there for some kind of quirky reason, but it's there. And there are a bunch of different things we can do when we're reverse engineering. What we try to do is to figure out, is there any way we can manipulate the memory of this program? Are there any buffers we can overflow? Are there any string format vulnerabilities? And we disassemble, decompile, and we develop our exploits. There are some prerequisites that you have to do in order for these things to work, because modern day computers have identified these problems a long time ago, because these are classical exploits. So there are a bunch of different things in modern operating systems that will try to prevent these things from happening. And one of those things is what's known as ASLR. That's not the thing with weird noises on YouTube, but it's address space layout randomization. It basically says every time you execute a program, the positions of your functions in memory will be randomized between executions, so you can't predict the memory addresses. So we need to turn that off because we are doing hacking. So this is a command you execute to disable that. If you don't do that, a lot of these labs you will do in a little bit won't work. There's also, when you're compiling native binaries, there's some compiler flags you can set to make them more vulnerable. So don't do this on systems you build for actual work or money, but do this for these exercises because it will make it easier. So we want to use the 32-bit memory mode because it's easier, the addresses are smaller. We want to disable the pi, and the pi is positioned independent execution. We disable that because that means the program will be always organized the same way after it's compiled. We also need to remove what's known as stack canaries. That is a defense mechanism that is built in to check the integrity of your stack during runtime. And if it has been tampered with, it would trigger one of these canaries that will tell the operating system that something bad happened. It shouldn't do that. So we disable that, of course. And for some of these, you will need to execute shell code, meaning you send in instructions to the stack that will be executed. And in order for that to work, you have to enable the executable stack flag when you compile your binaries. So that is that. And we do this because it makes it easier to do the lab exercises, and it also makes it easier to understand what's going on. It's not that it's impossible to do these kinds of exploits even if these things are turned on, but it's much harder and it requires much more work. So we do this to make it more concise and more predictable, so you will learn these skills. Let's talk a little bit about the x86 architectures, because we have a CPU. The CPU has a bunch of different instructions it can execute. It has what's known as registers, which are these little pieces where you can put in data, which the CPU will act upon using the instructions. And the x86 has this kind of quirky thing because it's a 32-bit CPU, but memory is segmented, meaning that it's divided into chunks rather than having a flat 32-bit mode of addressing. So for instance, the extended AX register is organized like this. We have the AL, the lower register, which is 8 bits. We have the high register, which has 8 more bits. And we have the extended register, which is 16 more bits. We have these different registers have different purposes. We have the accumulator register, which is this thing that usually accumulates data. We have the base register, and we have the counter register, which counts it's used for looping or decrementing and things like that. And we have the data register. And each instructions your CPU does uses these registers in a different way, and the only way to know what happens is to read the documentation and see how they are used. Then we have some special purpose registers, because these are general purpose. You can use these as you see fit. But then we have these ones, which is the pointer and index registers, which will be really important in some of the exercises. So we have the stack pointer that points to the top of your stack. Then we have the base pointer that points to the current stack frame you're on. We have the source index, which is used for string operations, and the same with the destination index is also used for string operations. Next, we have some segment registers, which is the CS, the code segment. That's the current program instruction your CPU is doing. Then we have the data segment, which is a general purpose memory operations register. Then we have the stack segment that points to the local variables, function calls, and all the stack management stuff that's happening. And then we have an extra segment. They just called it the extra segment because they didn't know what else to call it. But it's a general purpose register, so you can use for whatever you want. And another important one is the EIP. That's the instruction pointer, and that points to the next thing that will be executed in your program. Next, we have what's known as flags. These are bits that is set in a word that will tell you if something has happened during your execution. So you have the carry flag. That means if you have to do a carry or a borrow operation, it will set that to let you know that that happened. There's zero flag. That is if some kind of operations caused zero somewhere. We have the sign flag to indicate whether one operation resulted in a negative value. We have the overflow flag to see if some kind of arithmetic overflow has happened. Directional flag that controls the directional string instructions where you read your strings from. Intro flag to say is there any piece of hardware or anything that needs attention right now that's raised as an interrupt. And then we have the trap flag that's used for debugging actually, because if you execute code and you set a breakpoint, it's actually a CPU thing and an interrupt that's raised, and it sets that trap flag to tell the CPU to stop executing. We have the adjust flag to see if there's any borrowing that's needed to be done in the lower 4 bits of your registers, and the last is the parity flag to see if an operation has set an even or an odd number of bits. So the tools you're going to be using for these exercises is GDB, the GNU debugger. We're going to use pawn tools to build some different exploits. We're going to use Ghidra. We're not doing .NET, so .peek and ISLESpy is off the board for this talk. Another thing that we're going to use, because most of these services are hosted remotely in your CTF that you have downloaded, so you're going to use Netcat to talk to them, because not everything is on the web. Netcat is just this way of talking through a TCP socket to something directly, and you probably will going to use Python, because that's where Pawn Tools resides. And just to remind you of how the memory map for these applications work, the memory on your system works like this. So we have the high address space and the low address space. In between those, we have the start is the command line arguments and the environment variables. Then we have the start of the stack. The arrow indicates that the stack grows this way as your execution goes. Offset lower is the heap. That's your dynamic memory allocations, and then it grows in the opposite direction when you use it. Then we have some uninitialized data. Sometimes it's initialized to 0. Then you have the initialized data, and we have all the text that is part of your program. So let's look at some memory manipulation. Hopefully you all can understand simple C syntax, right? Anyone who feels that C is hard? Well, this is a C program, and it's a vulnerable C program. Does anyone know why it's vulnerable? Yeah, that's true. So we can see we have a buffer of 8 characters. And then we have a bool value that's initialized to false. And we output, please enter something. And then we run gets. And gets does no buffer size checking. It just will accept whatever the user put in as the input. So what will happen here is if the buffer is exceeded these 8 characters, that value will overflow and corrupt the rest of the memory of this running application. So let's take a look at what happens if that does. So this is the stack layout for that application. So we have the return address. Remember that this goes in the opposite direction. So that is the last thing on the stack. Then we have the base pointer that's saved. That's for your return thing. It tells the CPU where, once my function call is done, where do I return to continue execution. Then we have that buffer of 8 characters, and after that, that's that Boolean value. So let's just see what happens. Let's see if we can do this. Yeah, so let's check this out. So I've created this little program called Overflow. If I zoom in, you can see it's the same thing, only that the buffer is now 10 characters. We have bool that's set to false, and I try to get some input from the user. So if I run that GDB, so this is GDB. It's known as the GNU debugger. Can I zoom in? I can zoom in a bit. Let's see if we can do this. So okay, so the GNU debugger has a bunch of different tools. We can do info. That tells us different kinds of things we can get info about. We can also do, if I do info functions, it will show me all the functions that is part of this binary. So in this binary we have start. We can also see that it has main and it has a vulnerable. And these are all the library things it's linked to and it uses when it calls out to do its thing. But we can also do disassemble. So if I disassemble main, I can see these are the instructions that main is using to execute the program. So for some of you, this might look Greek and complicated, but it's not really that complicated. So we start by pushing the base pointer, and we set that in the stack pointer. Then we call this thing to set up your return thingy. Then we add this into the EAX register, and then we call the vulnerable function. Once we're done, we move 0 into the EAX, and then we return. That's the same as return 0. So main doesn't do much, it just calls the vulnerable function. So if I do disassemble vulnerable, we can see that vulnerable does a bunch more stuff. And what we can see here is that, for instance, we have this thing. It says load effective address of your base pointer minus hex 13 into the EAX register. It pushes that on the stack, and then they call gets. This is the address of that buffer. Okay? Then we do this thing, which is a comparison thing with the byte pointer to the base pointer minus 9 to see if it's 0. That is the if bool thing check. And if that is equal, it will jump to this position and continue execution from there. Otherwise, it will just skip that and go down. So if I run this, it says, what's your name? My name is Espen, and that's uneventful. It says, hello, Espen. It didn't do anything bad. But what I can do is I can set this I can set a breakpoint here. You do that by doing B and star and some kind of memory address. So I'm going to set a breakpoint right before it calls gets. And I'm also going to set a breakpoint before it returns, just to show you what's going on. If I run now, it stops execution. It triggers that interrupt. And we can now see that I'm here right now about to call gets. This is my stack at the moment. And since I compiled this with the debug symbols, we can also see the C code. That's not something you normally would see. But we can see we're here at line 11. We're just about to call gets. And I can also do info locals to see if there are any local variables, which I have. I have my buffer. It's initialized to some kind of garbage value because it's just random what's in memory at that point. And we can see we have this flag that's set to false. And if I continue the execution by typing C, let's see, that buffer was 10 characters long. So if I say Espen A, I'm now at the return instruction, which is implied here. So it's at the end of the curly braces. This is my new stack layout. And what happens now, if I check the value of those locals, you can now see that the buffer was filled up with Espen, but that extra A I put, that flowed into the flag variable. So 65 is the ASCII character for uppercase A. And if I now continue that execution, it will say that it will say that the flag is true. So I can now that I've built my exploit, I can do this in the terminal. I can do Espen A. And then it says flag is true, so that worked. So I overflow that buffer and overwrote some memory. So that is the simplest overflow thing you can do. So let's talk about something that's a little bit more involved. So this is what's known as ROPing. It sounds kind of bad, but it stands for return-oriented programming. So what you're doing is you have the same thing here. We have a buffer that is vulnerable because it uses scanf to read into that buffer, and it doesn't do any offset checking to see if that is the amount of bytes you have read in. But our goal in this thing is to be able to run this function called win. But as you can see, there is no place that win is executed anywhere in the program, so how on earth could we run that function? And that is where return-oriented programming comes into play. So what we want to achieve, we want to overflow this buffer, and we want to hijack this return instruction. So instead of returning back to the memory space that's after the greeting call, we want to overwrite that with the address to the win function. So when that return instruction is executed, instead of going back to main, it will jump to win and execute that. That is ROP, return-oriented programming. So you do that by doing the buffer overflow, but you also craft what's known as a ROP gadget or a ROP chain. And the simplest one is this one, where all you have to do is to figure out the return address. And this is how that works. So you have the base pointer that's saved, and you have a return address, and you have some kind of buffer you can overflow. What happens after you overflow that buffer? The data overflows into that return address and changes that address, and that gives you the ability to change the control flow of that program. So let me just show you how that works. Let's see. So I have this thing where I have this little program. Main sets it calls this thing to get a city, and it gets the weather. And what happens is that I want to be able to call this getFlag function. What I do, let me see if I can run this, Docker. This is not the example I wanted to show, this is a much more involved example. So this is the one I wanted to show, so sorry for that, for the confusion. We have this thing, so all I want to do is to run this win function. And I have this buffer that is 64 characters long, I call gets, and I should be able to overflow that buffer. Let's see that in action. So what I can do, I can do the same checks again. I can find my addresses. So if I run this once, it says something, and it didn't do anything eventful. But if I do info functions again, I can see now I have addresses for all the functions. So what we can do is this. So let's disassemble the vulnerable function. And what I can do is right before gets, I can set a breakpoint, and I can execute the thing. And I'm also going to set a breakpoint at the return address, like this. And what I will do now is I will continue execution, and it says enter something. So I'm just going to enter a bunch of A's to see what happens. Don't know if that is enough. Like that. So what happened now is I am at the return instruction, and I can see the stack pointer is pointing to 4 A's. So if I continue now, it will call a segmentation fault, and I will see that it says an invalid address with just those 4 A's. That is because there is no place in memory where those that address exists. But what I can do now is I can craft an exploit. So what I can do is I can run this program, and I can enter some input. Let's do Python, and let's, for instance, do like this. Let's do A. I can do times 64. And I can add. Let's add. That's wrong. You have to do print like this. Coding live in front of people. And I can add 4 B's, and that should run. And it should run if I add the last quote. So okay. So let's see what happens again now. Continue. I will see that I've written this to my memory, and if I continue now, it's enter something and it exited normally. So that didn't overflow anything. What if I do like 68? See what happens now. And I continue. I get a seg fault. It says bad instructions at this address. So now what I need to do is I need to craft this to be able to figure out how many characters I have to overflow in order to remove that return address. So that is what I want to do now is experiment with that number of A's in order to get 4 B's there instead. So if I go a little bit lower, let's try 70. Now it's could not read memory at somewhere, so it's not B's yet, so it's more than 70. Let's try 75. And this is the way you do this. You just so now I can see I have at least a couple of B's. So what about 76? See? Now I have 4 B's. Okay, that's good. Now I need to replace those with the address for the win function. And the win function, I can find that in memory, and I can find that here. So if I now take this and I replace the B's with that address, so it's, let's see, it's BD /61 X55 and X56. If I now continue that execution, I can now see that I've overwritten that return address, and it says that where is the thing? Invalid address. So it was almost 77. No, not yet. 6. Yeah. So what happened was I overwrote that return address, and it executed the win function. Let's see if we can see that again. on. Yeah. This worked. Yeah, there we go. Here you can see. It says, welcome to my challenge, congratulations, you win. So it was just me who had the wrong offset. So just to be clear, we're now calling get. If I continue, that input I generated gets inserted into that thing. And you can see I'm now at the return instruction, but you can see now the stack pointer. It has changed. It now points to win. And when it pops that off the stack and returns, it will, if I just step into that, it will now step into win. You can see I'm now in win. And since I changed the control flow, I'm able to execute that piece of code. And that's why it says, congratulations, you win, because we were able to do that. So I did that by just experimenting with that buffer to see where it overflows, to find the exact offset to align that memory address, which I did have to put in reverse because it's little endian, so we have to do it the other way around. And that points to that win function in memory. And that's how you do a ROP attack. So I will let you do now the binary exercises in your labs, and I will be here to help you, and then we will continue on to breaking web systems after your labs. Sure. If win requires parameters, you can do the same thing as you do when you're manipulating memory. You can just put more stuff on the stack, because there is no notion of arguments actually. It's just something that is expected by the calling conventions of your system. So when you make a call to a function that has 2 arguments, that is kind of this contract that function expects those 2 values to be on the stack. That's why you saw, for instance, that something was pushed into registers prior to doing some function calls. So it expects those to be on the stack. If they're not, then it will just take whatever it finds on the stack and tries to do that as arguments, which is why I think crash. And in those binary exercises, you'll find a link to a file. That's your executable. That's the thing you will have to figure out how it works and how to exploit it. And you need GDB on your system. You can also use another tool that's known as Ghidra. I can show that quickly. The Ghidra tool, that's a pretty fun one. So Ghidra is this reverse engineering tool from the NSA. You can just Google Ghidra. It's on GitHub. So it's this wonderful, wonderful tool that the gracious souls of the NSA has donated to the world. And of course, it comes with a bunch of warnings because it's not the most secure piece of software, but it's really fun. Let's see if I can find it. So let's see. And it looks like this, if I'm lucky enough to load it. There we go. So it's this wonderful piece of software. So if I check this, what I can do is I can insert a binary into this thing, and I've already inserted this ROP thing that I just showed you. And I can click on that, and I can use the dragon to open that up. And it does some analysis. And the cool thing is you can see the disassembly. So this is the disassembly of that thing. But the super cool thing about Ghidra is not only do you get the disassembly, but you get this pseudo-C thingy on this side that is basically code that's much easier to understand. So you can see it's the same thing. We can see we have some kind of undefined type. It's kind of quirky, so sometimes it does this. It's the main. It has some undefined value, that's the buffer. And it has this other variable, and it says welcome to my challenge with printf, and it calls the vulnerable function. Now I can go to this vulnerable function and see what that does. Here we have a local variable, that's the buffer, the other buffer that we're reading into. You can see it calls printf. I can also go into printf. And it calls gets and puts that into that buffer and return. So it's super cool. You can see all the instructions, you can see everything here, you can find the different functions. So here is the vulnerable function, here is win, and so on. You can also see the memory layout, you can see which libraries it's linked to, which versions of those libraries it's linked to, what different calls it does to the system, and it's a super useful tool for doing these kinds of things, and it's free for everyone. It doesn't cost a thing. There are some other tools as well you can use, like IDA. That's another tool, but that's not free. It costs a lot of money, but it does the same thing. Yeah, very limited. Yeah, if you're using IDA, you want IDA Pro, and that's the expensive one. But it's a cool tool as well. So let me just walk through one of these binary things that I will show you, because this is one of those format string thingies. So if you go to this Jedi mind trick thing and you open it, you will get a link to a binary. And what you can do is you can do the check on that binary to see what kind of file it is. So you can see that it's an ELF executable, and it's x64. It's dynamically linked to that version of the standard library, and it's not strips, meaning it has some debugging information. And this is one of those things that we can check out. So let's run that in Jedi mind trick. Come on, yeah. And we can do the same things as I did with the other one. We can do info functions to see if there are a bunch of functions, and we can disassemble main to see what's there. We can see that this thing, it basically calls random to get some kind of random thing. It calls printf to print out something. It flushes the buffer, and then it calls fgets to get something from you, and then it prints that out. And if I would use, I can also use Ghidra to make it a bit easier for me. So let's see. I can open that Jedi mind trick file, and Ghidra will do some analysis for me. Dragon will chew away at that binary and give me some nice things. Just click OK, and I can open it up with Dragon. So I think that the NSA people have some kind of humor, because all the dragons and animations and stuff in this thing is quite funny. So let's check out main to see what happens. So here we can see the source code that it has derived based on that binary. So you can see we have a bunch of flags that are fake flags. We can see that it uses the sram function to get like one of these by random, and it prints, it asks for your name, flushes the buffer, gets your name from standard in, and it says hello there, and it prints it out. And this is one of those, I'm sorry that I can't zoom in Ghidra. It's one of those things that for some reason doesn't work like the other things. But here we have, this thing is the problematic thing. It calls, I didn't want to do that. It calls printf with just the input buffer. So if I can actually rename this thing. If I do rename that variable, I can make that user input to make it more evident. It prints that out, and that's something that the user can provide themselves to that input. Meaning that if I run that binary, if I run that, and I enter in %s, it will just try to evaluate that as a string. So if I do, I can run it again, and I can do a p for a pointer, and it says hello there, 0x6022A0. That's the next memory address on that stack. And since I'm not providing the arguments, it pops that off until it finishes. But that also means that I can use a different kind of syntax. So if I do %6 and I do $sign and S, that says give me the 6th element of the stack as a string. So I do that, and it says, well, that was a null value. And I can continue doing this until I get to like something deep on the stack. So this time, this is one of my environment variables that it just popped off the stack because I asked for the 88th thing on the stack. So I exceeded the program space memory. I went into the runtime memory space and I found one environment variable. And that is why these format strings attacks are dangerous. So this little thing that was, let's see if I have that here. Let's see, workshop. I don't have that, okay. Anyways, so what I can do is that thing, it says something is on 2187, meaning I can do a netcat to localhost on 2187. It says please enter your name. I say Espen. It says hello Espen, I find your lack of printing disturbing, which is not a flag. But I can do the same thing here on the remote system. Come on. Okay, it's the demo ghost. Did I kill it? Yeah, it died. My computer died. That's fun. Everything died. That's great. Come on, computer. Do your thing. You have one job. Why? Why are you doing this to me? Okay, let's see if I can shut down the whole thing. Shut it down. Isn't that the thing you do? Turn it off and on again? Come on. Don't do this to me. I have more demos to show you. Okay. Let's see if this works now. Okay, good. Docker died. Okay. Runs. Okay, nice. Okay. Come on. Work. Okay, let's try that again. Localhost 2187. Come on, yes, enter my name. So I can do the same thing here. I can do 88, and I can get like the 88th element of that stack. And it says, strike me down with the power of strings. So let's do that. So I'm going to create a little exploit in Python. So let's see, how do I do that? Let's do code exploit.py. No. Come on, VS Code. I think VS Code is mad at me for restarting Linux. Come on. There we go. No. Failed to connect. I guess I will use Vim then. That's not what I want to do. Just exit this and see if I can make it work. It's web. Let me just cheat a little bit as well for the sake of brevity. Let's see. Yay, it worked, okay. So I'm going to use pawn tools to exploit this remote service. And I do that by importing pawn tools. It's a package, you have to pip install it. It's pwn tools. I will load the local binary as an exe file just to do some checks. But what I will do is I will connect to this remotely on 2187. And I will send a format string specifier from 0 to 200 and see what comes out the other end, basically. That's all I'm doing. So if I run that, Python solve I. Oh, there we go. Didn't save it, solve pi. No, it's not solve, it's exploits. There we go. So what it does, it dumps out the memory of that remote service and tries to interpolate everything as strings. These are the dummy flags that it chooses randomly from, that we saw from the source code. And after a while, I will leak into the environment variables, and one of the variables will be the secret flag that says the force is strong with this one. And that is how dangerous one of those string format things can be, because it's that easy to exploit. Hopefully you will have had some time to do one of these binaries, because now we're going to talk about the web. Because, let's be honest, these kinds of things with the binaries and such stuff, they are still relevant today, but it's usually in the lower layers of your application stack. It's usually your runtimes or your operating systems or your server code or something that you're using as a third party. Most applications these days are written on the web, because for some reason this guy, you know who that is? That's Tim Berners-Lee. He invented the web back in the 70s. He envisioned this wonderful place where every research paper and research data and things could be interlinked in this worldwide dictionary of, or worldwide encyclopedia of research, that you can always click links and find all the references and everything. And he created what's known as hypertext or HTML to do this, because you can have a document, you can link to another document. That was the idea. But the world decided that this is the most amazing application development platform ever conceived, so we decided to take that text markup thing and make it the primary application platform for everything from things that runs on your mobile phone to web pages on the internet to native apps in your operating system. I do believe that if somebody told this guy that you're not just creating this encyclopedia thing, you're creating the modern UI application platform that everyone will use from now on and forever, as what it seems, he probably would have made some different design choices. And the reason why he probably should do that is because the web comes with a heap of different kinds of vulnerabilities and exploits that can really bite you, as happened with me with the cinnamon bun story. So we have like cross-site scripting, SQL injection, we can poison templates, we can poison prototypes in JavaScript, we can misconfigure something, we can break our authentication even though we think we're doing it right. There's phishing and spear phishing things that happens, and there's also third-party vulnerabilities because we really love other people's code, because it's code we don't have to write ourselves. So for instance, if you're doing misconfigurations, what happens is that maybe we're enabling some unsafe features because we're debugging. Maybe we leak some details about our stack and our tools that shouldn't be known to others. Or we leak some data, and they are usually pretty simple to exploit. The same thing goes for the insecure design portions, because they are usually things that we don't know are there, or we are using tools in a way we shouldn't, or there's some kind of oversight, or there's some, you know the story. You pull a task from your backlog and it says, well, you have to do this by Friday, and you think, well, okay, I guess I have to do it since I pulled it from the thing, and you don't really have time to do it properly and well, so you do it as fast as you can. And that can have catastrophic outcomes. And they are easy to miss and overlook in your everyday job, but they are also easy to exploit. And some of these can be so mundane as forgetting to delete some files of a server that's available to everyone. And you're forgetting that all the search engines have these robots that crawl your site and find links to everything. This happened to me at one place I worked. It wasn't my fault, but one other dev on the team. We did some invoicing software that delivered e-invoices to like your mobile banks and stuff. And we had this feature that they wanted to implement because some users, they couldn't see their invoice in their app, so they wanted to have a PDF link to their invoice so they could view it in a PDF reader. And that dev thought, well, I'll just generate those PDFs and throw it on the web server and link to the PDF in the user's phone, which worked great. The users were super happy. The only thing that this developer didn't think about is maybe that should have been secured somehow. But since the scheme that these users needed to do to get this to work couldn't allow for any kind of session-based authentication, he thought, well, I'll just create some magic signed links that if you have the link, you will be able to open it, but if you don't have the link, well, then you can't read it because the code is in the link. What the developer didn't think about was this concept of web crawlers. So what happened was that all of these links were on the web server, and suddenly you were able to Google a name and an invoice, and you can find all your invoices or all the other users' invoices on Google, which was catastrophic because invoices tend to have some kind of sensitive data on them. Sometimes there's PIN codes to your accounts, or there's social security numbers, or your financing details and things like that shouldn't be available to everyone. And if one thing is that Google, they don't care about our little company. We try to like call Google up and say, excuse me, can you delete these things from your thing? They said, no. So what we had to do was file for each invoice that was structured. We had to file a request to have that entry deleted, and this was like 86,000 invoices that was leaked out. And that happened just because of this little design flaw. Then we have other things. In the JavaScript world, we have something called cross-site scripting, and that's where you allow scripts to be fed by users into your system somehow, and that can be used to steal data, manipulate other users' contexts, and or inject malware, or I've seen crypto miners and all sorts of stuff that's been injected with cross-site scripting. We also have a SQL injection, which is this classical thing that most of you probably already heard about. It's all about unescaped user input, where people are able to execute SQL scripts through the input, which can also be super catastrophic. And there's also this other thing this is the biggest thing in web development, is the third-party vulnerabilities, because we use frameworks, we use libraries, we use packages because we love them, and they do stuff for us. But sometimes that code is maintained by some retired guy in the middle of the wilderness, in the middle of nowhere, and we don't know that. We just love the library so much that we use it. And sometimes these things can be really vulnerable, and I'm going to show you some demos of that. So let's check out let's break some web servers. Hopefully this will work now. Come on. Okay, so let's do any Java people? Okay, a couple of Java people. Let's make fun of Java. I think that's fun. So we have this thing. So let me go on this web page. It's localhost 8080 in my case. It's not running. I should probably run it. Calculator. Let's run Disco. Let's run the serial one. That's cool. Now it should be running. So, oh, you're still seeing the presentation. Thank you. It's fun to do a demo and you're the only one seeing it. That is fun. So, okay. We have this wonderful, wonderful web page. Look at that design. It's so beautiful. It's about disco featuring this DJ called DJ Euler. And if you search that on Spotify, you will actually find that album with actual music. And if you find a way to download the music, you will find some secrets in the music itself. It's part of a CTF that we did a couple of years ago for Christmas. That's why it's Christmas themed. But this is a web page. And when we're doing web page hacking, we have some tools. For instance, there's one called What Web. And I can do the thing to localhost. Localhost 8080. And What Web would do some calls. It will check all the headers, and it will give me like this report of what it finds. Take some time. Come on, What Web. There's not that many headers. And it will give me some information about this system that I'm trying. While that is, there we go. So it found out that we are running Apache. We are running Apache Coyote, and it's called Santa's North Pole Disco featuring DJ Euler. So that didn't tell us a lot of things, but it says there's Java there. So I can try. Let me try to do something here to find something that isn't here. Not here. What happens? Okay, here we go. I get an error page, and that might seem fine. There shouldn't be anything there that's dangerous for me to know, but there is. Apache Tomcat and the version, which means now I know that I can search Apache Tomcat versions 8.5 vulnerabilities. Let's Google that and see what I can find. I can see there's this is a different thing. So let's check. Let's check. I have this prepared. So come on, read me. So there's this thing that is a treasure trove for CTFers or exploiters. It's what's known as the CVE database. That stands for Common Vulnerabilities and Exploits. And it's this database. Whenever some kind of breach is found and disclosed, they will go into, they will register it, and it gets this number, the year it was found, and some kind of serial number after that. That's the running serial number. And here we can see this vulnerability. It was discovered in 2017. It has been a part of Apache Tomcat for versions 9 to 9, 8.5 to 8.522, and 7. So it's been there a while. It also has this how severe it is. That's a rating. 8.1, that's something you don't want in your system. That means that somebody can really, really wreak havoc on your system. And let's look at what is this thing. So while running Apache Tomcat, if you have enabled HTTP put, it is possible to upload a JSP file to the server via a specially crafted request. A specially crafted request. That sounds difficult, right? Let's look at that specially crafted request. Let's see what I call it. Yeah, let's do that. Attack. So let's look at how specially crafted that request is. So it's a put and a body. That's all it is. And the reason this works is when they implemented the put verb on the web server, they took the specification and it says, well, put should either update or create a resource at the name you're referring to. So if I put this to localhost with this file name, the web server go, okay, do I have this file? No. I guess I should create it from this body you have sent me. And the developers of Apache didn't think about, well, where should we put that file? Should it be in the home folder of the web server where you can run executable code? And what rights should it have? Should it have the same as the web server? Should it be root? Should it be something else? Or should it be some kind of other directory? They elected for the first option. So if I run this, attack sh, and I will just show you, because if I do this pond, you can see that's not there. And if I execute this attack, and that web shell is basically, I can show you that as well, it's basically just a form that takes in a value, and then it uses that as a shell command and gives the output. It's super simple. There's nothing big about that. So if I execute that attack, let's see if I refresh now. It says OK. So now I upload that piece of code. And this is my little shell. I can use that to execute to see if I can find files on the server. And of course I can. And in this case, I'm looking for the flag or the thing, and it's there on the root folder. And this is now inside that server, inside that container. So I can cat out that flag like this. That's pretty fun, right? So I killed that cat. That's what it says. That's the flag. So I can exchange that for my points. But that's just this little misconfiguration that made that happen. I'm going to show you one more before we have to close this workshop. So this is one of my favorites, because this is another servers. I'm going to speed this a little bit up. So this is a web page. It's written in Node.js. I can find that with WhatWeb if I wanted to. And it says logged in as Santa. So if I check out my application, I can see I have this package cookie, which is this thing. Just go to serial. And that is a base 64 value. So if I echo that, and I echo that into base 64, and I decode it, I will see I have this structure. So you can see this is JSON, right? So what happens if I take, what happens if I take my POC, where I just changed it? So, oh, it's the wrong conference, but pay no attention to that. So I changed my name to Espen and the country to Erde, because that was the conference I spoke at last time. And if I do that, if I just cat that out to POC, maybe I can do like this. I will get that base 64 string. I can copy that. And if I replace my cookie and do refresh, I'm now logged in as Espen. So that might seem mundane, right? But if we investigate this web page, you can see there is no front-end JavaScript. So that evaluation of that JSON object, that has been deserialized on the server side. And then it has used some kind of templating language to replace this value from that structure. And if you're a new Node developer and you want to serialize stuff, what do? Well, you Google node serialize. And then you find this. There's a library for that. Awesome! Even though serialization of JSON object is natively supported by Node, why wouldn't you use a package? Do you see anything wrong with this thing? It's broken, but it says serialize an object. Yeah, that's also true, but it still has 2,520 weekly downloads. But look, it's function into JSON. Why on earth would you serialize behavior? You should never do that. That's not what serialization is for. And the reason is JavaScript is a quirky language because it has this little thing called an immediately invoked function expression, meaning if I do function, some kind of anonymous function, and I do console log, I do hello, cool people, and I invoke that function, it will evaluate that function, invoke it, and just give me the output. So if I do that, it says, I probably forgot something. Yeah, I forgot a paren. Like that. So, hello, cool people. That works. So what happens if I check this repository? I will see how it does this. And first thing, it says, on the GitHub itself, it says, this is so unsecure, please don't use it. But I released it to NPM, so I can't remove it because I don't know what depends on it. But please don't use it. And here it says that syntax for serializing a function. So it has this prefix that tells it's a function. So what happens if I do this thing here, where I say bat, come on, bat exploit. Yeah, so here I have that thing, and I say, please execute this function where I call a TCP pipe to a listening server that I control, which I hopefully have up and running in my Hyper-V environment. Let me just check that. Come on, Linny. So here we go, and I just have to check if my come on, if config. Oh. Yeah. Come on. Let me just stop that. Start it again. That usually works. Just need to make sure the IP address is the same I have in my exploits. Because it makes more impact if it actually works. Come on. Everything, all of these demos were prepared, but since everything crashed a couple of moments ago, everything is now not set up correctly, which is a shame. I'm sorry about that, but that's the way things are sometimes. Come on. Okay, I'll show you another one. What would have happened in this case is it will call that server and I will have a reverse shell. Let me just show you the last one instead. That's the calculator one. This is a cool one. So this is a thing where I'm also using a library. If I do, this is a calculator, it works just like a calculator. And I can do variables, and I can say C equals B plus A, and I can execute that. And I will get a reply back, and it says it uses something called math.js. And math.js is another flawed library that allows something called prototype pollution. So let me see if I can do calc. Come on. So what happens in JavaScript is if you want to replace a constructor function, you can do that by calling the constructor function on that base object, and you can give it a new body as text, and it will execute and replace that function. So if I add this, I will see back I get 1. That's the one. That means I can execute code. So for instance, if I were to try to get require, so I can load other pieces of code into the context, I can do that, but that doesn't work. Thankfully, in JavaScript, there's pointers to things all over the place. So if I do this by getting through the main module to see if require is part of that context, I can find it. And this is what happens when you do toString to a function. It will dump the function body as a string. That means I can spawn child process, and I can do basically this. I can do this thing to spawn a synchronous process and list out some files, which is pretty fun. So I can use this calculator and execute the files remotely on the system. So these are the files on that server. And if I did some more digging, I will find out that by executing bin bash, I can find the flag. It's part of the server code for the server itself, and I can just grep to it to find it because it's running Linux. And I will find that as part of the source code through the interface itself, which is pretty neat. That's because Math.js has this flaw. So yeah. Well, you have your labs. You can do them at your own time where you want to break into these web services, because we're now out of time for the workshop. Hope you enjoyed yourself, and I hope you had fun, and I hope you're inspired to learn much more about offensive security and go home and test your systems and try to break them, because that is how you build better systems. Thank you.